Good morning, chemistry fans. Welcome back to AP Chemistry live streaming lessons. This is Sean Byrne here. I'm excited to have you back. Just because the last time we were together, I was sharing my weather reports. Everything is beautiful and sunny here in outside Chicago, Illinois. I teach at Glenbard West High School, remember, outside of Chicago in Glen Ellen. Today is Tuesday, April 21st, 2020. We are going to start our conversation of Unit 7 on equilibrium. As I was preparing today, it really seemed like so much of this is review. So to say that we're starting our conversation of this seems a bit strange because we have looked at a lot of the principles that are at play here in equilibrium. Throughout the course of these lessons, we're coming kind of to the end of our review material, and next week we'll be looking at some FRQs for you. So a lot of the themes today are going to seem very are going to seem like review for you. And if that's the case, that's great. I really want to make sure you have a good foundation of the theory behind equilibrium, maybe not as much with the math. We will do some of that. And then as you're looking back through earlier lessons on acids and bases and several other topics, you'll see where a lot of the math that we've been looking at comes through. Our daily reminder of where to go if you have any questions on apstudents.org/exams on any of the information over here on the right-hand side of the screen. We've got our calendars highlighted and a big target on Thursday, May 14th. At whatever your local time is for this AP Chemistry date. Remember that we'll have a 45-minute exam. 25 minutes for first question and 15 minutes for the second question. The first one will be 60% of the weight and the second question will be 40% of the weight. And this is really going to be a skills-based exam. So as we look through a lot of our materials today, what we really want to be trying to do is explain chemical phenomena, draw conclusions, analyze systems, and support our claims with evidence, and make sure that it's not just about getting an answer per se, it's about being able to explain how and why we got that answer. So our lesson overview is the same as always. We'll start with a warm-up for today, run you through a couple of what you need to know and give you some opportunities to practice those skills. Feel free to stop at any point and review or solve a problem that's right in front of you. And you should have a scratch piece of paper and a pen or a pencil and probably a calculator at your side if you can, because that's going to help you to be able to review all of the work that we are doing today. Okay. We have lots of topics that we're going to go through today. I've kind of chunked these into groups of two so they don't get too overwhelming, all around this topic of equilibrium, so that we're feeling really comfortable with this going into some of the more complex parts of it tomorrow with Mr. Faribaugh. All right, so our warm-up is a review of the homework problems that Mr. Faribaugh gave us yesterday. And so the first question asked us to look at this experimental data where we have an oxidation reduction reaction that is listed up here at the top. Na2S2O3 is reacting with NaOCl and some sodium hydroxide. We have our concentrations and volumes right here. And so the question asks us at the beginning, nice review question, kind of get us warmed up, get our feet on the ground, make us kind of build up our confidence when we're solving problems like this, right? Is to determine which reactant is a limiting reactant and to justify our answer. And so what we're going to want to do is compare what we have here in this solution to the ratios that are necessary given to us in the balanced chemical equation. We give us a little bit of a hint there. That's where we should look. We're going to look at the ratios of the coefficients to one another. So I'm going to just start out by noticing that all of the concentrations and the volumes are the same. So we really only need to do one concentration or one calculation here. The scoring guidelines don't ask us to necessarily spell out this calculation, but for me, I just feel better having the numbers in front of me and to practice this idea that moles is equal to molarity times volume, which of course comes from the definition of molarity as moles divided by volume. You notice that I converted volume into liters here. So 5 milliliters is the same as 0.005 liters, and our concentration stays the same. So in effect, we have 0.0025 moles of all three of the reactants. Okay, so I just put those in a chart so I could compare what is required stoichiometrically from the equation that we have 1 to 4 to 2 as our ratio of moles to one another. What we actually have is equal numbers of moles of everything. And because we're going to use 4 moles of NaOCl every time we use 1 mole of Na2S2O3, and every time we use 2 moles of this, the NaOH, sorry, the NaOCl is going to run out first because we're going to use it at a much higher rate. We're going to use 4 moles for every one of the other and 2 of the second. So that one would run out first because we have equal numbers of moles of everything to begin with. Okay. Part D asks us to analyze a graph. So this is a good skill. This should be a pretty straightforward skill for you, but we kind of need to know, I guess, what part of the graph we're looking at. So we want to know what's the temperature change for this reaction. So we're going to look at the difference between our initial temperature, which is down here. This is a really good exercise in making sure we read the problem carefully. The problem told us that the original temperature was 20 degrees Celsius. Now, if we read it carefully, we would see that this is clearly at 20 degrees Celsius, but we might want to just confirm that from the information that's given to us. It'd be a silly thing to make a mistake about. And then I would read this graph as about 32.5, okay? You certainly want to be above 32. You certainly want to be below 33. This line right here, the solid line would be at 33. The solid line below our curve is 32. So you'd want to be in between those two. I would suspect that there's probably a plus or minus 0.1 here. So it looks pretty close to the middle for me. So I would put this at 32.5. If you had said 32.6 or 32.4, I'm sure you're pretty close. If you had said just plain 32 or plain 33, you probably would have gotten some points taken off of there. We know that we can, because our measurements are to individual into the ones place, we want to estimate a little bit beyond that, right? 1 decimal place beyond that. And then our temperature change is just going to be final minus initial. So 32 minus 5 minus 32.5 minus 20, excuse me there. And we get a temperature change of 12.5. Now would be a good point also to just kind of remind yourself, all right, the temperature went up when this reaction was happening. So this is happening in a probably in a styrofoam cup or in a beaker or something where the temperature is going to be controlled really well. A calorimeter here, that's an insulated calorimeter. There we go. So definitely not a beaker then. An insulated calorimeter keeps the temperature all contained within that calorimeter. And so if the temperature is going up in there, that tells me that this is an exothermic reaction, that when our chemicals got together, we go back over here, when our chemicals get together, they release energy, tells me that that's an exothermic reaction because the temperature is going up. We don't necessarily need that to answer this part of the problem, but we would probably need it later, and it's just a nice thing to remind ourselves as we're moving forward, okay? Next part asks us to calculate the magnitude of heat in joules that is released during the reaction. So we assume that the specific heat is given to us here. So I always like to use the specific heat as a way to remind myself of our units. So we have joules, grams, and degrees Celsius here. So my equation is going to be Q is equal to MC delta T. Many of us say MCAT, but however you put it in there, this equation is given to you on the test. And this C, specific heat, fits in here, and our units are kind of told to us in what we need to use for our mass and our change in temperature. So we can just plug in our 15.21 grams, which is given to us in the problem, our 3.94 joules per gram degree Celsius times 12.5, and we get Q that's equal to 7.49 joules. Okay, so here our units are consistent with what it's asking us to do. We've got 3 sig figs, which looks pretty good there. We're not concerned about a sign here. This is the heat absorbed by the calorimeter. Okay, and so we are going to say that this is the amount of, or the amount of energy that's released by the reaction. So we don't have to worry about a sign here, and we'll leave it as positive. We're going to look to the next part, right, where we're going to say, using the equation, we want to get the delta H of the reaction in kilojoules per mole of reactant. And we need to include the appropriate sign here. And this is where that conversation that we had earlier, that this is an exothermic reaction, is going to be important, okay? We know that the number of moles, we already calculated that from the first part of this way back at the beginning of our lesson, okay? So we know that this is the number of moles of NaOCl that we have to begin with, okay? But we need to divide that by 4 because our balanced equation said that for every one time that the reaction runs, we use 4 moles of NaOCl. So we're going to divide our total number of moles by the number of moles of reactant to get 0.00625. And then our delta H is just the amount of energy divided by the mole, our answer from up here, okay? Now notice I did 2 things to our energy here, I made it negative, okay? Because in this case, we're again going to have that conversation. This is an exothermic reaction. That means it's giving off energy, would feel warm. We saw the temperature rise. And then I also changed it to kilojoules from what was previously joules, because our question asked us to report our energy or answer in kilojoules. Okay, so this is just where you're just being very careful in your reading. The math here is not necessarily complicated. It is just making sure we keep track of signs and conversions between joules and kilojoules. And we end up with an answer of negative 1.2 times 10 to the third kilojoules per mole. All right, and that would be our final answer for this question. Lastly, very nice, typical AP question. Magnitude of enthalpy calculated from the results is the same, even though what happened? That we doubled the volume of each of the reactants. How can we explain this result? So here, go back to what I said to you at the beginning of today's lesson. We don't want to rely just on being able to solve good mathematical problems. We want to be able to explain what's happening in the chemical reactions in front of us. And so what I notice is happening is that I'm doubling the volume. Concentration stays the same. So that means that I have more of each of the reactants. Well, of course, that means that I'm going to make more energy as well. And because our delta H is a ratio of energy to the number of moles that react, the ratio will stay the same. The energy goes up and the number of moles go up. Okay, so I might write something like this: when the volume of reactants is doubled, the number of moles of reactants is doubled as well. This causes the amount of energy to double, and the delta H remains the same because the ratio of energy to reactants is the same. Okay, so that would be one way you might answer it. If you did want to do something a little bit more mathematical, this was the second response that was given in the scoring guidelines, that the second experiment, we have 2 times MC delta T, okay, because we've it divided by 2 times the number of moles, and that equals the twos would essentially cancel out, right? 2 over 2 is equal to 1. And so we would end up with the same delta H. The magnitude is the same as the calculated. So our numbers might be different, but because this is a ratio, we're going to end up in the same place. Okay. So let's get to what you need to know and give you some practice as we're going through these today. I'm really going to take a big step backwards in talking about an introduction to equilibrium and the direction of reversible reactions and things like that, and then get into a little bit of the math. Like I said, I doubled these up just for simplicity's sake as we're going through this, so that we have a little bit more focus on what we're doing, and rather than jumping between these. Obviously, all of the topics run together in a pretty significant way for a lesson on equilibrium. Okay, so I want you to think about a container that just has only water in it, and maybe some air above it, but it's a closed container. Now, we've looked at a couple of examples of this, whether we were talking about a eudiometer, whether we were talking about vapor pressure and in gases, in Dalton's laws of partial pressures, things like that. But we know that if we close off a container like this, that a certain number of particles are going to evaporate, right? And that they will continue to evaporate until there are enough particles above the container that some of them will start to condense again. So we start out with, if there was nothing, when I'm looking at this picture right here, there is very little in that, very little water in the space, water vapor in the space above the liquid water, right? And so more and more particles are going to evaporate until we get to the point that there are enough particles up there that they can start to condense again. And that what we will see is that we will eventually get to a point where the number of particles that are evaporating and the number of particles that are condensing is equal to one another. And what we would call that is equilibrium, right? So this is an example of an equilibrium that is with evaporation and condensation. This is a physical change, just the particles evaporating and condensing, but it's a dynamic equilibrium because the number of particles that is evaporating and the number of particles that's condensing would be the same. Now, this is a very simplified version of what's happening here, right? But I think that the principle is a good one and makes sense as an example of what's happening for equilibrium. Now, be careful here in remembering that this is a closed container. Okay, if you were to have an open container, what you know is that the particles would evaporate, and then they would move throughout the entire room. They would disperse throughout the entire, diffuse throughout the entire room. Okay, in Chicago in the winter, it gets really dry. The air gets really dry, and so we have humidifiers in our bedrooms to keep us from getting sick. Those humidifiers use this principle by having a fan on the top and blowing off these particles so that you continually have particles that are evaporating. Equilibrium happens in a closed container like this because the number of particles are staying close to the surface of the water. And this is something that would happen. This equilibrium is achieved in the closed surface with a in a closed container at the surface of the water. Okay. Now a similar thing could happen with I left the words evaporation and condensation in here. I'm sorry about that. This is would not be evaporation condensation. This is for a salt that's dissolving, right? So this is particles. If I put a solid into water, and I would have some solid particles that are dissolving into the solution, okay? And similar, here we go. At the beginning, we have a rate of dissolution that is much larger than any sort of precipitation. We just have particles that are dissolving into and filling up the liquid, moving around until we have a solution, until we eventually get to a point where we have so many particles that some of them will again start to precipitate. Okay, and when we get to what we call a saturated solution, especially if there's particles at the bottom, the rate of dissolution and the rate of precipitation are equal to one another. Okay, so we would just see this dynamic equilibrium where the number of particles that's dissolving and the number of particles that is precipitating are equal to one another. Now, you've also seen equilibrium anytime you've used an indicator. So I kind of got stuck in a YouTube tunnel last night looking at videos of the blue bottle experiment. And if I had the materials here at home to run this for you, I absolutely would. I don't have them, but I encourage you to look at this. There's a pretty great example of equilibrium between oxidation and reduction, between indicators. When we have just this one hydrogen on this big, huge molecule of methylene blue makes this entire molecule colorless. And when that hydrogen is removed, when this whole molecule is oxidized, just that one hydrogen gets removed, this turns into a blue solution. And so we can play with the fact that these are two different colors by increasing the amount of oxygen in the container, increasing the amount. There's all sorts of different variations on this experiment that are really cool to watch. But you are probably familiar with looking at any sort of indicators in acid-base reactions, right? And those are examples of equilibrium as well. We know that if we are using, where's one that we might be, phenolphthalein is probably something, phenolphthalein is probably one that you're used to. You have a colorless solution at a pH roughly less than 9, and then right at 9, it starts to turn into pink. So if you're doing a titration, you might have used phenolphthalein. You might have used other indicators to look at different changes at other pHs. Okay, and so when we talk more about titration, we'll talk about which indicators are the best to use why. But the idea that we can change this molecule back and forth by adding or subtracting protons or by adding acids and bases is a great example of equilibrium and how the molecules can switch back and forth based on what we have there. I would imagine that many of you have seen a picture or a graph that looks like this. And this is kind of the classic example of what happens in equilibrium, where we have a gas, N2O4 and O2 are in a closed container. Okay, an evacuated container just means a solid container that had nothing else in it, right? Some of it is put in there, and then the concentration is measured over time, right? So we started with 10 moles per liter, or 10 looks like 10 to the negative second moles per liter of N2O4, some of the reactants, and 0 of the products, the NO2, and measured the concentrations of each of them over time. And what you notice is our concentration of reactants goes down, but it doesn't go down to 0. It doesn't just finish off down here. It levels off at a point where we have a concentration of some of the reactants, and the concentration of the products increases to the point where we have both a example, or we have some concentration of reactant here and product here. Many students will think that when we say equilibrium, what we mean is that we have equal amounts of reactants and products. And that is a really, really big misconception. You can see in this graph, there is a moment right here where we have equal amounts of reactants and products. However, that is not the moment of equilibrium. The moment of equilibrium, or the time at which equilibrium is reached, would be about 60 minutes here. And then beyond, it stays in equilibrium. You see that the concentrations of the reactants and products do not change at all. Okay, the amount that we have here stays the same, they stay constant, and that would be an example. That's the definition of what happens in equilibrium. Okay, we can measure the rates a little bit here. We can see that the rate at which the reactant is getting used up is, it would be a negative rate, but the magnitude here and the magnitude at which the products are being made is different, and that's because of the coefficients, right? We see that we have coefficients, a coefficient of 2, so there's 2, I know the concentration here is going to go up much more quickly than the concentration of the N2O4 goes down. But eventually they even off, and we get to the point where we have 0. We have 0 change in concentration. The rate of the forward rate and the reverse rate are equal to one another. Another example of this, and we see a lot of these graphs in different textbooks, is I was doing research, and I'm sure that you have something similar to this in your own researches, where we're looking at the reaction of SO2 and oxygen to make SO3. I don't know why that says CO3, that should say SO3 right there. Obviously, what I would like to compare here is how we started, where this reaction started. Okay, we had some of our reactants and none of our products. So this would be similar to that earlier reaction. Okay, where we have only reactants, no products, and we end up at equilibrium. Okay, and here we have none of the reactants and some of the products, and we end up in the same spot for equilibrium. We have equilibrium reached here. We have a consistent or a constant amount of reactants and products. Now this is dynamic equilibrium still. We still have reactions happening back and forth and back and forth. However, the forward and the reverse reaction are equal to one another, and so we do not have an overall change in concentrations here. Okay, so this would be another very common experiment, or a common equation that you would see. I hope that my head up here is not cutting off the fact that we have a reaction of carbon dioxide and water, carbon monoxide, water to make carbon dioxide and hydrogen. Wanted to point out just a different way of looking at the same thing. Here we have, for trial 1, what our initial concentrations of everything look like. So we have some reactants that we're going to put into, again, a closed container that would have nothing else in it. And after we have let it reach equilibrium, we notice that we're going to have some concentration of each of the species, both reactants and products. We could do a different experiment where we start with only the products. So this would be like that second graph we just looked at. And we would end up with a reaction. We would end up with a mix of reactants and products at equilibrium. Okay, we're going to get to in just a minute how all this math might work out and look at each of the specific concentrations in there. I'll tell you how we might calculate each of those things, but just for right now, I'd like you to see, as we're starting out with, in this experiment, only reactants. We end up with a mix of both. Here we end up with products. We end up with a mix of everything. Here we could start out with a mix of everything, and we end up with a mix of reactants and products. Okay. Something interesting happens when we put all of these graphs on one axes, that you see that the overall number of overall concentrations for these are gases, so the overall pressure in there is not going to change, which we could compare back to Dalton's law of partial pressure, which we looked at earlier on this in these reviews. So you see that the overall number of particles the concentrations are staying the same. So really like this graph just as an example of multiple different ways of looking at where we start, but how we would always end up with a mix of everything. And I'm about to tell you, I think you can probably predict what the mathematical value of these numbers are, how we could get those. Okay, so just to be very clear with you before we move on to that math, like I said, when equilibrium is reached, the reactants and products are simultaneously present. And that's what we saw, excuse me, just for 1 second, that's what we see here. At equilibrium, reactants and products are simultaneously present. We have 3 good examples here. We're not saying that they're present in equal amounts, we're just saying that they are all present. Okay, the concentrations or partial pressures of all species remain constant at equilibrium, right? There's no observable changes to the system. So from the outside eye, even though we can draw some nice particle pictures of particles evaporating and condensing, or we could have them dissolving and precipitating, that we're not going to see that inside of a container with just the naked eye. Okay, but we know that those things are still happening. And what that means is that the equilibrium state is dynamic. The forward and reverse processes continue at equal rates, resulting in no net observable change. So these are just kind of the bullet points of what we mean when we say equilibrium. And we've done a lot of math with it, but I think it was important for us to spend a couple of minutes just looking at exactly what the equilibrium position means. Okay, and so then we can get into this idea of either a reaction quotient or an equilibrium constant. Mathematically, we would typically say that we are looking at products over reactants, right? So if this is our general equation up here, where we have the small letters are coefficients, and each of the capital letters is some sort of chemical. Okay, we can look at Q, and Q is what we call the reaction quotient, and that's a quantity that we can calculate at any time. We're given a set of data and we want to know something about what the ratio of reactants to products is, we can calculate that Q. We oftentimes will compare that Q to what we call K, which is the equilibrium constant. KEQ is typically reserved for equilibrium constant for concentrations of reactants and products. And then KP, we can talk, would be about partial pressures, but you can see that if these are gases, this would be partial pressure. Sometimes you still will be given gas quantities in concentrations of a container. Excuse me. So just being comfortable with the idea here generally throughout all of these is that we're going to look at concentrations of products over reactants, and that any of the coefficients are going to be exponents on our calculations. Okay, so let's just look at what that might look. We're given an equation here. We're told what the value of K is, and we're asked to calculate the reaction quotient and then to determine if we're at equilibrium and then how the system will proceed to get to equilibrium. Okay, so I'm going to write out my equilibrium. I'm going to start with a Q, equilibrium constant, where I have N2, the concentration of N2, the concentration of H2 raised to the 3rd power because of the coefficient here. Okay, and our divided by the concentration of ammonia, NH3 raised to the 2nd power because there's a 2 on that equation, right? The 2 is the coefficient on our reactant. Okay, so I could plug in my numbers that are here. My concentration of N2 is told to me to be 1. My concentration of H2 is 1. My concentration of NH3 is 0.2. Okay, and you want to be very careful with how you put this in your calculator so that you get an answer that is 25. I think it's exactly 25. It's not even a rounded number. And so what we can say, we're going to compare, right? This is our Q. This is our K as told to us. Our Q is greater than our K. So that means that we have more reactants than we would need at equilibrium. And so our system will proceed in the reverse direction. Okay, we're going to compare, we're comparing our Q, right? We don't know if we're at equilibrium. It's told, hey, here's what we have. Here are some measurements we have. Is this at equilibrium? No, it's not, because Q is not equal to K. And we can even go further to say that the system will proceed in the reverse direction because Q is greater than K. All right, so here are 3 other examples that I'm going to ask you to stop and look at A, B, and C. Let's say that if you are the oldest, you should do letter B. If you are a middle child, you should do letter C. If you're the youngest child, you should do letter D, or just pick any of the numbers that you want to do here in order to get some practice. Go ahead and stop the video just for a second. And then I can go through each of my solutions for each of these. Okay, so for number 1, I said that our Q is equal to 0.222. Our Q then is less than K, so it's going to proceed in the forward direction. For letter C, we end up with a 0 on the bottom here, right? You see that there's a 0, and typically I think we define dividing anything by 0 as approaching infinity or getting close to infinity. That's important because it means that we have a really large number. We can say Q is greater than K, so the reactions can proceed in the reverse direction. Now I would point out here, we should know it's going to proceed in the reverse direction because we have to have, if it's at equilibrium, if this is a system that wants to get to equilibrium, one of the things we said is we have to have some of all of the reactants in the products, right? So if we start out with 0 of these reactants, okay, our concentration is 0, we're going to go in the reverse direction to make some of those, right? So that definitely makes sense that we would want to fill in this 0 by moving in the reverse direction, okay? Last one, we got all 1s in there. The math there is pretty easy, sorry, letter D, friends. But making that conclusion, we got to a Q that's equal to 1, so the Q is less than K, so it's going to proceed in the forward direction. Okay, I hope that those calculations made sense to you. Let's just look at an even simpler version. If we are given, here are the concentrations at equilibrium. So a general equation of A, 2 A's plus a B makes 2 C's. These are all gases. Okay, we're given a container that's a rigid evacuated vessel. This means it's solid. The volume's not going to change. There's nothing else in it. We are the container is injected with enough to make a 0.01 molar concentration of A and B and C to begin with. So you can think about that graph where we might have all 3 of our points at the same spot on the y-axis. Okay, and then we're going to see what happens to our concentrations at equilibrium, right? So we're told this is the concentrations after an unknown amount of time. We're not concerned with the amount of time it takes to get to equilibrium. We just are concerned that it is at equilibrium at this point. Can we calculate the value of K? Well, sure we can. We know that K is equal to our concentration of our products squared. Notice we've got a square here because of the 2, the coefficient, divided by the concentration of A times the concentration of B, but we're going to bring down this coefficient of 1. You may want to just be in the habit of bringing down all of the coefficients, right? So if you have a 1 here, that 1 would be filled in right here. Yes, it's not going to hurt anything to have a constant exponent of a 1. We would fill in our numbers here. We should get to something that is like 0.88. Okay, now it's important to remember that concentration is K is going to be constant, but only constant at a particular temperature, right? So we might be given a set of circumstances with the same experiment where it's repeated at a higher temperature. Kc, we're told that is found to have a larger value. Okay, so describe the effect of the temperature change on the concentration of the gases in the equilibrium. So what can we say if K is larger? Take a second to stop the video and just jot down a couple of notes of what can you say if K ends up being having a larger value. And I would say a couple of different things. I would say that a larger K means that we have more products. Okay, so we're going to expect there to be more letter C's or product C if the K is larger. Concentration of A for A will be twice that of B, right? So this is going to go up by go down by twice the value of B. If we're making Cs, we're going to go down by a lot more because the stoichiometry here is 2. And that the changes in magnitude for A and C would be the same because of these coefficient here, but they would be opposite in direction. So we're going to add C and we're going to lose some A. This is, again, some explanations of some of the things we might see for this kind of a reaction. Okay. The last thing to remember about the reaction quotient and equilibrium constant at the same time is that they are we would not include any substances that are not in the same state as everything else. And typically that means that we're not going to include solids and pure liquids. And we've seen multiple examples of this in our work together as we've been doing ice tables. I didn't even include a single ice table today because we've done so many of them. But you know that we typically, in an equation like this, so here's the combustion of methane. If we're making liquid water, if we said that liquid water was produced here, that would not be included in our K expression, okay, because it is liquid, because we have 3 gases here, we have no, and this is a liquid, so it would not be included up on our K expression, okay. Why don't you go ahead and take a look at this. This is another example where we have multiple different states of matter. What's our K going to look like? This is a very unusual one in that we have no denominator. So we just have NO2 to the 4th and O2 to the 1st. Both of these are solids, and so they would not be included in our K expression. So here's 2 examples. One, a complicated base problem. Just want to give you practice of that. We've looked at some KBs over the course of our lesson, so you should be sort of a review for you. And then here's a solubility problem. We're looking at a solid dissolving into its components. Take a second, pause the video, and see if you can write just the K expressions. Don't have to do any calculations, just write the K expressions. And for both of those, I would have made sure that I eliminated the liquid from our beginning, or from our first one, right? So we just have, this is actually a base. Here's its conjugate acid, making some OHs. And then I'm going to exclude the solid, and we call this a KSP, solubility product constant, because this is a solid here, and we include our 3 because we made 3 nitrates in there. Okay. Now let's just go in real quick into a conversation about the magnitude of equilibrium constant and a couple other quick properties. You may have seen some charts that look like this. I like to just show these as an example of, you know, how many substances have Kas or Kbs. We'll look at some KSPs in a minute, but we can see the wide range in values for each of these. Okay, and so this is a really, really tiny number. 1.8 times 10 to the minus 12 means that it's 0.11 zeros and then 1/8, right? So that's a really, really small number. And so what that tells us is that for hydrogen peroxide, okay, this is what we would call a very reactant favored substance. Okay, that there's not a lot of products, that the numerator, the number that's on the top, is going to be very, very small. The number on the bottom would be very big. And when we divide that out, we end up with a really small number. And we could compare that to iodic acid up here that has a relatively small number, 0.16, but in comparison to 1.8 times 10 to the minus 12, it's a really big number, right? By a magnitude of 11 here, the difference, that's a really big difference, okay? And so we would say is that this is much more product favored than the hydrogen peroxide is, if we're going to compare our iodic acid to a hydrogen peroxide. And we could do a similar thing down here with our bases. This number for aniline, 7.4 times 10 to the minus 10th, is very small, especially in comparison to diethylamine. Excuse me. Same thing for solubility product constants. Again, you would never be expected to memorize any of these things. Okay, this is just for, you know, these are reference guidelines that are you can look up at any point. I just wanted to give you an example of, like, look at Bi2S3. I'm amazed by this. 1.6 times 10 to the minus 72, right? So really, like, incredibly small number. Okay, and then we could compare that to, you know, 5.0 times 10 to the minus 3rd. Like barium hydroxide, something we probably talk about it being pretty insoluble in water. We'll compare that to bismuth sulfide. Is that how we would say that? Bismuth sulfide, how we would compare those two numbers is just sort of incredible. A couple of these down over here as well. Okay, so the magnitude, the number here is going to tell us a lot about how comparing our reactants and products. So this would be it could be a typical AP problem that you could get. You're given two equilibrium reactions at a specific temperature. You see that it's given to you there. Told you how this is set up. Okay, based on the fact that we're going to add the same amount of moles to the containers, what can we tell about the concentrations of bromine chloride or NO gas, nitrous oxide gas, as compared to one another based on our KEQ value? So pause the video here for just a second and see if you can come up with a good solution to that. And I think that the best thing that you could say here is that the amount of bromine is going to be way more than the amount of NO, right? Because it has a much larger KEQ. So the much larger KEQ for reaction 1 means that you have a lot more reactants than you have products. And these, any of these kinds of problems would absolutely just be comparative problems where we're looking at comparing the two KEQs of one another rather than just kind of an arbitrary number off the top of your head. Okay, and you would have to be given these numbers or given a set of data to calculate the numbers and then make a comparison, right? We could certainly do that, but you would never be expected to memorize numbers like that. Lastly, just looking at a couple of different properties of what we can do if we're gonna play around with these equilibrium constants and put some reactions together. This feels a lot like Hess's law, which is something that we talked about with Mr. Fairbaugh yesterday. Where he was talking about, you know, in this case, reaction 3 was your goal reaction or your the reaction that we're trying to get to. So if we're going to say that reaction number 1 has a K that looks like this, and reaction number 2 has a K that looks like this, can we compare how reaction 1 and 2 look to reaction 3 in order to come up with a good with an estimation of what how K3 would look in comparison to K1 and K2. Okay, so the chemical equation, here's the two that are given to us. What are we going to have to do here to our values up here to get to K3? Well, one thing would be maybe we just write K3 based on our numbers here, and then we compare it up here. What I'm going to do is I'm going to look at, similar to what we would do in Hess's law. Look, I have some methane as a product in reaction 1, but it's a reactant in reaction 2. I have 1 water. I've got 2 water, so I'm going to have to worry about that in a minute. But look, some carbon monoxide. Oh, I'm going to have to probably get rid of that. Some hydrogen. So it seems like I'm going to have to reverse the first reaction. And when I do that, then I'm going to have to reverse the second reaction as well. And by reversing it, that'll get all 4 of my hydrogens to the product side. I'm going to end up with 2 waters on the reactant side. And by reversing them, by reversing the reactions, I'm going to reverse the, take the inverse of the K's, right? So when a reaction is reversed up here, our rule is that the K is inverted. And then if I add reactions together, the K's of the resulting overall reaction is the product. Okay, so the simpler way to say this is that K3 is equal to the product of 1 over K1 times 1 over K2. Okay, so this is just doing, this is a pretty classic AP type question that has nothing to do with numbers, which actually makes it a little bit harder, right? Because it's much more conceptual. So we have to kind of think through what's happening here. When the stoichiometry coefficients of a reaction are multiplied by a factor of C, K is raised to the power of C. So that's sort of obvious, I think, that if we looked at the difference between reaction 1 and reaction 2, right, when we add these coefficients, so this is the same reaction just with larger coefficients, so we've doubled everything in reaction 2, we could rewrite this as K1 squared. Okay, that our exponent properties would just allow us to factor out that 2 by making it an exponent up there. Okay, so once you take a look at this, this is our last guided practice problem for today, where we're looking at 2 reactions are given to you. What would be the correct expression for the equilibrium constant for reaction 3? Pause your video if you need to. And as I was looking at this, I got K3 is equal to K2 over K1. And I think what that means is that we reversed reaction 1, but we left reaction 2 where it is. Okay, so double check my work there and see if you're able to do that on your own. All right. So that's our lesson for today. Lots that we ran through, a lot of theory kind of at the beginning about just making sure that we see that equilibrium is more than just ice tables, and that it appears in a number of different places in chemistry. And that's really important, I think, for us to see that equilibrium really spills over into gases, acids and bases, into solubility in lots of different places. And so I wanted to give you examples of those and give you a good picture in your brain of what's happening there. Okay, why don't you take your new skills out for a ride on 3 practice problems that we have for you today. Take a screenshot of this. You got, if any of that's cut off at the top, it's the same setup as before, but what I'm asking you to do is say, do you agree or disagree with the statement below based on the graph that is there? Statement says the reaction was about to reach equilibrium at time equal A because the concentrations of X and XY were almost the same. So do you support that or not? And give us a short explanation of why or why not. Here we'd like you to draw a particle picture. We've got equal moles here. So here's time equal to 0. Time is increasing as we go from left to right. And what we'd like you to do is to draw a particle picture in box T, or box for T equals 400 seconds, that's consistent with the conclusion that equilibrium was reached for this reaction after 300 seconds, but before 400 seconds. So somewhere right in between here, we got to equilibrium. Okay, and so what would the particles look like in this box in order to say that we got to equilibrium? All right, and then lastly, right off of the 2017 test, write an equilibrium expression for a reaction as it's given to you there, and then calculate the value of K based on the K expression that you got based on the information that is there. Okay, this one looks like you might need to have an ice table to set up, but you may be able to do it in a different way as well. So have fun with that. And Mr. Faribault is going to have a solution to that for you when we come back tomorrow. All right. That brings us to the end. Our good reminders to keep checking apcentral.collegeboard.org. Look in the links in the description below for extra helpful chemistry resources. And then continue to reach out to your friends, family, anybody that you know that needs some extra help with devices or with internet access. We're asking people to go to this site, cb.org/tech, by this Friday, April 24th. So it just gives you a couple of extra days. Please make sure to reach out to that, even if you're not sure of all the information. And to just get that process started is going to be really important. Thanks so much for watching. Have a great day, and we'll see you tomorrow. Thanks much.